So, welcome to the circuit analysis series. Now we are going to study and learn about the mesh analysis. Loop or mesh analysis is the circuit systematic technique that we use to analyze different kind of circuits. So it's a dual of basically nodal analysis. So in the nodal analysis, like if we have a circuit, we try to find the voltages at the different nodes. Okay, then using those voltages, we can calculate the currents, voltage drop, whatever is required as per the circuit requirements. In the loop or mesh analysis, we are going to find the loop currents. Okay, like if we have, for example, a circuit, let's say this is a circuit, it has two loops. So we are going to find these two loop currents. And once we find those loop currents, then we can find the rest of the required. Okay, for example, the voltages across the different branches, the power dissipated, supplied, etc. So this is the key difference between nodal and mesh analysis. Let's have a look at the first example. So we have a circuit and we want to find the current I naught, okay, using the loop analysis or mesh analysis. So I naught means the current that is basically flowing through this resistor 6 kilo. If I look at this circuit, I can solve the circuit using nodal analysis also. Like we define the different nodal voltages, different nodes here. Like this is the first node, this is the second node, and this is the third node, okay. We can define the nodes, we can write the nodal equation, and then we can find the required voltages, and then using that we can find the current, okay. So using nodal analysis, we can say that basically I naught could be written as, like if we have found the V naught, so V naught minus voltage here 0 divided by 6k. So I can get the I naught using that technique. So now let's have a look how we can solve this circuit using the loop or mesh. So whenever you want to solve any circuit using loop or mesh, the first thing is identify the loops or closed paths in your circuit. For example, in this circuit, we have two closed paths. A closed path is, for example, if I start from this node, I can move this side, then through this resistor, then through this resistor, and I can come back here. So this is one closed loop. Similarly, like if I start from here, go back towards this side, then come back here, then come back here, this is the second loop. So you need to identify how many loops or meshes in your circuit you have. After that, you will define a loop current for each of the loop. For example, for the first loop, we define that the current that is flowing through this loop is basically I1, okay, and the current that is flowing through this loop is basically simply I2. So identify the loops, define the currents that is flowing through the loop. You can define any direction of the current, but it is advised to follow a systematic way. Like typically, we define the current is flowing in the basically clockwise direction, like here. So once you have like drawn the loop currents, identify like what you are going to name them, like I1 and I2. This is similar like in nodal analysis, you name the nodes, okay, V1, V2, V3. So here we label the currents. After that, what will we do? We will write the KVL equation, okay, for every loop, okay. Like we have two loops, so we are going to write two KVL equation, Kirchhoff Voltage Law. So if you guys can recall, we wrote basically the KCL equations in the nodal analysis. So to write the KVL equation, for example, for the first loop, we know the direction of the current. You can define the polarities. Okay, current is flowing from clockwise, so this will be positive, this will be negative, and this will be positive, and this will be negative. Now we can write the KVL for this loop. So starting from this, okay, like this voltage source, so I can write like -12. So KVL is basically the sum of all voltages drop in a loop is basically is equal to 0. So -12, then the voltage drop across 6 kilo ohm. So it's a resistor. So using Ohm law, V is equal to IR. Voltage drop across any resistor will be current multiplied with the resistor value. So the current that is flowing through this resistor is I1. So I can write that plus I1 times the value of resistor, that is basically 6K. Then plus, again this plus sign. Now the current that is flowing through this resistor 6 kilo ohm. So if we look at this resistor 6 kilo ohm, through this two currents will be flowing, okay. one current will be I1, that basically will flow like this way clockwise. This is I1. And the second current will be I2, that is basically also flowing clockwise. But for the resistor 6 kilo ohm, this current will be flowing like this one, I2. So net current that is basically flowing through 6 kilo ohm resistor with reference to the first loop, that will be basically I1 minus I2. So always when a branch, resistive branch is shared between the two loops, the current through that will be the difference of the loop currents. So I can say that through 6 kilo ohm, the current is basically I1 minus I2 times the resistor value, that is basically 6K, is equal to 0. So this is our first loop equation for the first loop. Once we are done with this, we will move to the second loop. Okay, so the second loop we have here, we will follow the same approach. Based on the flow of current, we can define the polarities. So like current is flowing plus, minus. Similarly, we can put plus and minus here. Okay, so the current is flowing like this way, positive to negative side. So let's say I'm starting with this point, okay, the source voltage. So I can say that basically plus 3. Then I move to this point. Now what is this here? Positive sign. Okay, so I can put the plus here. So now because I2 is our reference, loops 2 current is our reference. So that's why with respect to that reference, we put the polarity here positive. Okay, so it means now I2 is flowing like this way and I1 is flowing like this way. So because of this reference, now the net current through 6 kilo ohm will be I2 minus I1. So I can say that the voltage drop across 6 kilo ohm is I2 minus I1 times 6K. We are done with this one. Then we come here, then again plus. What is the current flowing through 3 kilo ohm? That will be basically I2. So I2 times 3K is equal to 0. So this will be our second loop equation. So remember to not confuse between the polarities, okay, that we are getting for this case. Okay, for the first loop we wrote the current I1 minus I2, and for the second case we are writing I2 minus I1. Okay, this is based on the reference of the loop that we are using. So in the first case we were using the first loop, so this was our reference, so we consider that this is a high current. So that's why we write it I1 minus I2. When we move to the second loop, so that's why I wrote it I2 minus I1. So now we have two loop equations. Okay, now just we need to simplify this using the same technique like we did for the nodal analysis. So let's rearrange it. So if I rearrange it, I can write this as minus 12 plus, so I1 times 6K plus I1 times 6K and minus I2 times 6K is equal to 0. So further we can say that I1 together, so basically I have 12 I1, okay, then I have minus 6 times of I2 is equal to, so minus 12 will go to the other side, so I have basically this simplified equation. Okay, so the K you can include it, or basically at the end we can divide with K, that will just make the current say milliampere. So here what we can do the same thing, 6 times of I2 minus 6 times of I1 plus 3 times of I2 is equal to 0. Or if we rearrange it, so minus 6 times of I1 plus 9 times of I2 is equal to minus 3. So that will be our second equation. So we have basically two equations with the two unknowns. Okay. Now what we can do here, we can simply solve these two to get the value of the currents. So you can use different techniques, okay, again like nodal analysis. Let me just use the substitution. So I can bring from here, like I can write that 12 I1 basically will be equal to 12 plus 6 times of I2, right? Or simply I1 will be 12 will be divided, so 1 plus 6 over 12, that will be 1 over 2 times of I2. Okay, so I can plug this one within this equation. So I have minus 6 times of I1. I1 is what? 1 plus 1 over 2 times of I2 plus 9 times of I2 is equal to minus 3. So it means this will be what? Like if you just do the other multiplication, minus 6. Okay, so that will be minus 3 times of I2 plus 9 times I2 minus 3. So 9 plus minus 3, that will be 6 times of I2 minus 3, and this 6 will go to the other side, it will become plus 6, or basically minus 3 plus 6 is 3. So it means I can say that I2 value will be 3 divided by 6, which is basically simply 1 over 2 milliampere. Okay, so this current basically comes from after solving the loop 2 equation. Okay, now we can put this one, okay, here within this equation, and we can get the value of I1. So that will be 1 plus 1 over 2 of I2. What is I2? 1 over 2. So that will be 1 plus 1 over 4. Okay, or we can say that basically simply I1 will be, what is 1 over 4? So 1 over 4 is simply 0.25. So I1 basically could be written as 1.25 milliampere. Okay, so we got the value of I1 and we got the value of I2. Our target was to find the value of I0, okay, in this question. So we can simply basically write I0, okay, I0 is basically just nothing, current through the resistor R1. So I can write this as I1 minus I2, okay. So we can easily find that I0 will comes out to be I1 minus I2. So value of I1 is 1.25 and the value of I2 is 0.5. Okay, so 1.25 minus 0.5, that comes out to be 0.75 milliampere. Okay, or 3 over 4 milliampere. Okay, so this way we can find the current I0 for this example. So we write the loop equation, simplify them, get the currents. So loop analysis will give us the currents through the loops. Then using that we can find whatever else you want to find. For example, if you want to find the V0, so V0 is basically the voltage drop across 6 kilo ohm. So we can simply write that V0 basically will be equal to nothing, 6 times of I0. So you know the value of I0, which is 0.75. So 6 times 0.75, that will be equal to 4.5 volt. Okay, so once we know the current through the loop, we can find anything else that is required for that particular circuit. Thank you so much.